Hey, how y'all doing?
Good. How are you?
Great question. How am I? Some days it feels like you get stuff done and you still have more to do. How about that? We'll go with that. 10 after time to start up. I've got just a couple things that I thought I would want to mention to y'all administratively as we're heading in towards this next exam. And maybe if I share a screen, that's a good way to go. And let's go with that guy. And I'm going to share a screen. Let's pull that guy out front. Assuming I can figure out what I'm trying to show to you. Okay. Okay, I thought I had it all perfectly set up, and yet no. Okay, so where is that thing I was going to share with you? Okay, well, I'll just sort of enter through the back door. Good. Okay, so showing you something, and let's just do student view so it looks closer to what you might be looking at normally. If I look into week 4 here, I seem to be changing up some of what we're doing in week 4 in minor ways because of the speed that we are going through the material. And with an exam coming up and with I guess next week being the last week, where exactly things can fall best into the course timing wise, it's going to be a little bit on the variable side. So change gears a little bit. And today I want to talk about this thing called a partial F test. And there's a lab associated with that. And then we can put and that's a lab that we have to do before we do any of the content that is really important for next week. And so this week is great. And today before chapters 8 and 9 is probably a good idea because the chapter 8 and 9 content is for most of you pretty straightforward. And this thing called variable selection, that's probably going to be next week. We'll see where we get tomorrow in class. Okay. And so Thursday this week, you're going to be getting ready for this test that I'll release Thursday, probably about 5 o'clock. And you can work on it at any point in time, as long as you turn in before Friday at 11:59 p.m. And so work back from the amount of time you have for the test. It's going to be formally a 50 or a 55-minute exam. I'll probably make it 55 minutes. So that way you can, again, take some scratch work if you've created some scratch work and you want me to see it. Sometimes it's hard to like type things with Muse and Sigmas into a little chat box. And so maybe you just rather write it out by hand. And in question, say 7, you could say, well, please see my answer that I'm going to upload or that I have already uploaded. And I could look at that to determine how you should be scored. Okay, so that's something that I think an extra 5 minutes is fine for. Just make sure you get it done. Okay, so with that as the backdrop, y'all may have questions of an administrative nature, and I know I have at least 2 emails from y'all that I haven't answered today, and I think one from even last night late that I haven't yet been able to address. And so if you want to raise the issue in the email with me, just raise it now. That's absolutely fine. Do want to say one thing about the lab scores. We're still working on getting that fixed. I shouldn't say fixed like it's your mistake. It's not. It rather is I didn't set things up in a way that required you to sign into lab groups earlier on. And so if one of you uploaded the lab in your group and there's names on it, we're all good. I'm going to go back later and make sure that those are all properly updated before any final grades are determined. So don't be worried about the lab scores, but beyond that, there still may be some administrative questions that you'd like to raise. So now's a great time. Let's do it.
Do you know when you're gonna release the sample to solutions for the second exam?
Great question. I don't have a plan of that, but I would certainly hope it would be before Thursday morning. I have them mostly, if not completely, written already, and it's just a matter of me doing that. Are you saying that you have already looked at them, Anthony, and you sort of want to know what the answers are?
Not complete, not entirely.
Okay. Because if any of you are in the situation where like you're saying, I'm already sort of done and I'd like to look over the answers, just let me know and I'll upload them sooner rather than later. But I figure by tomorrow morning or tomorrow about noon should be sufficient for all of you to sort of get some 28 hours worth of looking those over before you'd ask questions in class on Friday. Someone else, maybe? Okay, what about questions that tie to things on recent, I shouldn't say recent labs, as though we had one last time, but things that were in recent labs or homework that you would like to chat about? Any subject matter questions? Okay, well, I'm not going to worry about that so much. Questions do show up sometimes in office hours, and that's absolutely great. I do have to say, though, asking questions in class is absolutely fine, too. Some classes are like that they don't really want to ask a lot of questions during class time. Others really want to spend a lot of time on the subject matter questions, and that's fine either way. Okay, so let me maybe move this off to the side and get into this thing called the partial F test. And essentially, a partial F test is a situation where you're saying to yourself, you know what, I fit a complex model. There were lots of parameters, if you will, slopes or effects that we included in our model. And we would love to be able to have some, but not all of the betas zeroed out. The reason we'd like to have some, but not all of the betas zeroed out is going to be different from situation to situation. But the lab sort of walks you through one situation where that's going to be very clearly what you would need to do to tackle a problem. I want to show you a slightly different situation in class. And so to motivate, let's just talk about our broccoli data from the Santa Maria Valley. And these are, again, in number of days since the plant was seeded, or I guess we put a seed into the ground that will eventually form a plant. We have information on the root length, which is no surprise that roots grow across time. So the roots for, 50 or, 102-day roots are a little bit longer than the roots if they were only, at 32 days. Okay. For whatever reason, I chose to model the square root of the root length. So I'll call that root. I think exploring data graphically is always a great place to start. Okay, so let's get after that. And within GMP, I'm going to want to use Graph Builder. So under Graph Builder. The square root of the root length might be different across the amount of time. And there is this little one oddball data point, 2 individual data points at 123 days after seeding seem to have no roots. And so we included them in the data set. I say for the sake of analyzing these data, I'm going to do something that I think is kosher from my point of view. Of the plants that are living, let's just look at just those. So I'm going to sort of like highlight You notice that you can highlight certain data points and it sort of turns them on inside or selects the rows inside the data set. Yeah, that correspond. So I'm going to highlight just these a couple data points and note that, yeah, they have a 0 length root. I'm just going to choose to hide and exclude these values. So ignoring those 2 data points where we have the root system not formed, okay? So I would say it looks as though, to me, maybe let's highlight all of the data, make it darker. It looks as though there may be an approximately linear trend relating the amount of days since the plants were planted to the square root of the length of the root system. And the reason I did the square root of the length of the root system, we'll see in chapters 8 and 9, the topic that's for tomorrow. It straightens out that scatter plot, makes it look perfect as opposed to sort of like bent. And also it avoids a problem of lack of equality of spread in the residuals and another problem, a lack of normality in those residuals. So like 3 birds, 1 stone, let's go kill it. So I'm just going to use the square root of the root length, and here is my smoother. The thing though that we talked about when we discussed these data the first time is there's these 1, 2, 3 different cultivars. I guess if I show them in red, green, and blue for well, red ink, green sim, and blue con. I don't know what those names are, but those are just 3-letter abbreviations or the name. If I show you with those different colors, it's really hard to tell, other than maybe the blues are a little higher off to the left here, and less likely to be seen below the line. So blues, if we have 1 trend line shown, blues would have a residual that tends to be more positive than the other colors. If we took the color and made it an overlay, if you will, you can see we have a little bit of separation, that this sim varietal has smaller roots at the days under, at least 90 or so than the blue con does. And maybe eventually we have the con and ink having really similar trend lines, and maybe it's a little bit different than the sim variety. So we've got groups, and as we talked about recently, you might want to fit a model that takes that grouping information into account. So under Analyze Fit Model, I'm going to go ahead and say, well, the square root of the root length, good. Depends on the days since seeding. And I'm just going to go with cultivar. I'm going to fit a parallel lines model for the moment. There's no particular reason that's where I think I'm going to end up. I'm just saying, are there even 3 noticeably differing groups? And in the analysis that I fit, I've got here our cultivar, 3 of them shown in different colors. We've got the blue down low, the red and the green up higher. One question I have is, hey, are there 3 separate groups? Are there maybe 2 different groups, and maybe the green and the red lines are like a 1 common trend line, or is there just 1 trend line overall? Our summary of fit, let's just blitz past that analysis. Let's go right to our effects test. The effective cultivar says in the effects test, having controlled already for a trend line relating days since seeding to the root of the root length, we see a difference across at least 2 of these 3 groups. Okay, like we did 3 class sessions ago, you could say there's an adjustment to the intercept, and not all of the intercept adjustments are the same. Are they all the same? Are they all different? What's going on? We'd say at least 1 is different than the others. So at least it looks like blue and red would be differing from each other. Beyond that, I don't know. We could, if we wanted to, and I'm going to go through this with under estimates. Oh, I'm sorry. Darn it. Okay. I'm looking for where the Tukey procedure is here. And I'm not seeing that so quickly. No, multiple. Oh, it's under multiple comparisons. Under multiple comparisons. Let's use multiple comparison across the cultivars and use the Tukey procedure. We could say essentially, are these groups differing from each other? And I would say con and inc are differing from each other. My confidence interval for, I'm sorry, con and sim are different from each other. And then inc and sim are different from each other. Con and inc, I cannot say are differing from each other. So perhaps two of the groups have a common trend line. Con and inc may have a common trend line, but the other two, the other group is noticeably different from each of those first ones. So that is a great question. Okay. So that's step one in our discussion. Preface. Step two is to consider our indicator parameterizations. And this is something that our lab today walks you through. I'm going to say we've got different cultivars, and JMP will tell you by default, it's going to use that sum to zero parameterization style. Sometimes there are conveniences of using the indicator parameterizations. And so to get those dummy variables or indicator variables that correspond to the indicator parameterization, we could simply click into or highlight the whole column that corresponds to the variable that we would like to have indicator values for. Now that I've highlighted the cultivar here, I could under columns say, you know what, I would like under utilities to make indicator columns for the three cultivars. Yeah, literally, I want three new columns, one that tells me, are you sim or not? One that tells me inc or not, one that tells me con or not. And I usually like to go with this append column name, and you don't have to. I often will select that just for my own sake. In this case, I don't need to. And we have these 1, 2, 3 new columns that correspond to which cultivar is it. You can see, well, con takes a value of 0 if it's not a con. The con variable takes a value of 1 if it is one of these con broccolis of inc. I was gonna say inc similar, but that'd be too funny. Inc is similarly, if we had an inc level of 1 in my inc variable, it is of the variety inc. If we have a 0 here for inc, it's not. Similarly, sim, we have a sim correspond to a value of the sim variable as exactly 1. So these three categorical, I guess this one categorical variable cultivar, which gives me three different groups, I can say, let's break it down into, are you a this or that? Are you a this or that? Or are you something else or that? So and I'm thinking, if I tell you if you're con or not, 1 or 0, and whether you're inc or not, again, 1 or 0, you sort of know whether you're sim or not. And then furthermore, across these first two columns, you know indeed which cultivar you are. Okay, so let's get back into the analysis that we had just fit and see that there are two that look perhaps similar. Okay, and darn it. I think I'm going to go ahead and fit this analysis all over again. So fit model here. We say that the square root of the root length, root, may depend on the days since seeding. And I'm just going to go with cultivar and fit that 3 parallel trend line model. And as before, you can see we've got these 1, 2, 3 groups that seem to want to stand out as differing from each other. The Tukey procedure says we don't really know that all 3 of them are really differing from each other, but our effects test or adjusted sum of squares says at least one is different from the others. Inc and sim were the 2 that we spotted were perhaps quite close, or I shouldn't say quite close. those were the two that I think look, okay. Red and green. I'm saying red and green, con and ink may be the same group. Perhaps con and green may be the same group. And the question is, how do I model whether things are the same across all three groups, two groups exactly and not a third, or are there three separate groupings? Okay. I want to compare three separate models. Okay. And again, I'm sort of thinking that ink and con might be, I'll say similar. That's sad. Okay. So if I were to fit a model like I just done, and let me turn on for fun my indicator parameterization estimates. You're saying that if it's con, it's a little bit higher. If it's ink, it's a little bit higher. But if it's sim, that is my reference group. If I were to fit a model with my dummies for con and ink, I can get the exact same output. So let's go ahead and try that multiple regression, where I'm going to use, recall, instead of cultivar itself, I'm going to say, are you con or not? And are you ink or not? Again, I'm choosing the same two values here as I see in my categorical variant of the model. Okay, run that. And in, well, okay, let me smallify. And in my output, then, I don't have this nice graph, darn it. I do have, for my summary of the fit, an R square value. Let's see if our R square value here is the, heck, it is the same. Our root mean square error, the same between two models. Our analysis of variance for our model that we fit with 3 degrees of freedom, it has an F ratio of 76.5. 3 degrees of freedom, F ratio of 76.5, same p-value. I bet you we fit the same model. Let's go ahead and look even at our indicator parameterization estimates. We have an intercept, same thing over here. Days since heating, same slope. The con effect, well, it's now a slope for con, because the con variable is 0 or 1, and the only way for it to increase by exactly 1 unit is to go from a 0 up to a 1, from a non-con to a con, and the second one from a non-ink to an ink. That's really effectively comparing, are you con versus are you that reference group, that sim group, or not? Okay, so con and ink, I'm fitting the exact same model two completely different ways. Okay, so what do we want to do now with our model? Well, what if we didn't use both con and ink? What if we wanted to allow, again, one of the groups to be similarly similar to the others? And darn it, I keep losing my graph. Okay, Kendall, yeah, I got a question.
Yeah, I'm just curious why, because you didn't put the sim column into your model, why didn't that change anything?
Yeah, great question. The reason is sim was the reference group that the software chose for me. I love your question because I can redo my analysis. Let's go ahead and redo it entirely and say, let's have recall. I'm going to have, instead of con and ink, I'm going to have con and sim as the two separate explanatory dummy variables, the indicators. And if I were to do that, zooming in a little bit, darn it, zooming in the right way to the part of the analysis, same R squared, same F ratio. The intercept is now different. The slope of DSS is the same. The effective con and the effective sim are different than before. But interestingly, this guy here, which said ink is 0.19 higher than sim, We're now saying sim is 0.19 lower than ink. We're comparing to the ink group. So Kendall, did I get towards answering a question, or would you like to rephrase it, or what? What do you want to do with that?
I think that's good. Thank you.
Okay. But we talked earlier as though not all three groups were different. And I'm going to say not all three groups are different. I don't know. All three of them are differing from each other. Are there two which stand out as differing from each other, and then the other one might not be different at all? Okay. If I want to do a reduced or differing model, I could choose to fit the model with, instead of DSS, con, and sim, I could fit the model with DSS and just sim alone. And that would be using con and ink together as that reference group. It's fitting two trend lines, one for each of the two groups, the sim group, and then the other two lumped together. Okay, so when we do that analysis here, we can say, you know what? I've got a differing model now, and certainly sim is different from the other two, but I don't know if con and ink are differing from each other. In the first one we fit, we didn't see if con and ink are noticeably different from each other. We said con is different from sim and ink is different from sim. Here we're saying sim is different from con and ink, and shoot, that 0.34 higher. Con is 0.34 higher than sim. Ink is 0.2 higher than sim. We're now saying sim is 0.3 or so lower than the other two. Is this model about as good as the first one we fit? We're essentially wanting to compare the two models, and we can't do so exactly using any set of analyses other than by comparing this guy and this one. So let's zoom in on the things that I think are probably important. So in our analysis of variance in the summary of the fit, this is a 0.46 R squared. This is a 0.45 R squared. I don't see much difference in the R squared at all. Okay. Along the same lines, the sum of squared errors here was 46.5, and now the sum of the squared errors is 47.3. That SSE, not much different at all. Maybe this model here with just a sim versus non-sim contrast is going to be just as good as the model with 1, 2, 3 groups. Two groups, there's sim and then the other two. That might be describing things about as well as the model with 1, 2, 3 groups. So that was a long and rambly bit of discussion of, you know what, sometimes there are hypothesis tests that you can get after by dropping 1 or 2 or 3 of the variables. And when you drop the variables, all you got to do is compare the sums of squares error of the two different models. So let's define a couple terms. SSEC, SSE for the complete model, the model with more variables in it. MSE for the model that's complete, the model with more variables in it. Let's bigify so you can all read this better. Okay. We also have a reduced model, a smaller model, a model with fewer terms, a model with fewer parameters that we need to estimate. We've removed a variable. Maybe it was one of the dummy variables, but this SSER is the sum of squared errors for the reduced model, the model that corresponds to the null hypothesis, in fact. The null hypothesis says, hey, the reduced model is sufficient. You don't need the other parameters, the other variables that you dropped. And for that null hypothesis, let's see how much there is a benefit of having that complete model. And if the reduced errors are quite different from the complete model's errors, then I'm thinking Well, this F ratio will be tending to be large in size. Again, if you have a huge difference in SS error, that's going to say, oh, the model is now, much more important. No, I shouldn't say it that way. If you have a huge change in SS error, the complete model is noticeably better. This F ratio is SSE of the reduced minus SSE of the complete, that natural sort of difference of how well we're doing, divided by the change in degrees of freedom in our model, divided through by MSE for the complete model. And there's numerator and denominator degrees of freedom. And you can literally get from a JMP macro, and I'll show you that macro in a little bit, you can get those calculations done real easily. And let's go ahead and try this here in the context of a different data set. And I want to use the data set, not that one there, but and I think you have the slow homes. Let's go ahead and use the data set that you've been plugging away at with your what is it? Duncan's data on the occupational prestige. Okay, so occupational prestige, D for Duncan. There we go. Okay, here we go. There is the data that we have. And again, you might be comparing two different models. Okay. And we indeed believe that income may be related to prestige. There are three types of careers. Okay. Education. We're ignoring that for the moment. Graphically, the model that we're fitting is something along the lines of prestige. How does it depend on the income? And does it do it separately for each of the types of careers? Let's phrase it this way. Is there a difference across these 1, 2, 3 groups at all? Is there a difference at all that could be attributed to either there's a difference in the intercept between the groups or a difference in the slope between the groups? If there's a difference in the intercept or the slope between the groups, you'd say the groups are different from each other. I'm really going after, are the groups different from each other? So I'm going to write down this F ratio, and then we're going to sort of work it out in the context of these data. So I want to make sure I still have the data lying around. I'll move it off to the side so that way I can bring it back. So what we're going to do is fit two models, and I'm going to go with, again, let's take type of career, and I've highlighted the whole column. Under columns, I'm going to say make for me, under utilities, make for me some indicator columns. And I'm going to say, let's go with the column name appended. So that says like, oh, it's a type BC, or it's a type professional, or it's a type white collar. And again, you don't need all three of these. Any two of these would allow you to say there is, allows you to know which group they are from. And I seem to keep removing my graph. Okay, so I'm thinking, and I could be wrong here, but I'm thinking, let's call the blue collar group the reference group, because perhaps the green group is only a little bit lower and the slope is only a little bit off, and maybe the red, again, only a little bit off from the blue. I'm going to use blue collar as that reference group for my analysis. Okay. So let's go ahead and do our analysis. We need for the model, we're going to go ahead and have the prestige level, boom, determined by the income, and also whether it's professional or not, and whether it's white collar or not, right? So far, so good. And for the moment, I'm going to put the interactions on hold. I'm going to say, let's run this model, and let's hit run. Okay, so income is predicting prestige, and we are going to have professional and white collar as the reference groups. Run that analysis. If you will, this is a complete model. The model with the blue collar and the model with the not blue collar, the model with the professional, and then the white collar dummy variables. Okay. And you can see that, well, the professional seems to be noticeably different from the blue collar group. We have our sums of squares error and mean square error for the complete model. If we had fit the model without those two dummy variables, again, under analyze, fit model, drag it over here, recall, that worked right now. But if I don't have the dummy variables, boom, I could go ahead and run that analysis. And I have a simpler model that I just fit. It's only got one intercept and one slope. So it seems like it's got a larger sum of squared error than we used to have. Larger sum of squared error says to me, well, probably at least one of the two terms that I dropped, the professional, in terms of its difference from blue collar, or the white collar in terms of its difference from blue collar, at least one of these two adjustments to the intercept was necessary. So I can have complete model upstairs and reduced downstairs. And I'm going to go that. Upstairs, it's complete, reduced is downstairs. Let's go ahead and figure out, okay, and then there we go. Upstairs is complete, downstairs is reduced. And I'm going to go ahead and write down, maybe even let's move it further over so we can have just off to the very end, that third, the second number listed is the error. It gives me more space to work with. Okay. Let's talk about our calculation of the F ratio. And I'm going to start by just writing down things that I know. For the complete model, okay, we've got SS error equal to, well, for the complete model, it's got a 41 degrees of freedom error and 3 model degrees of freedom. So I'm going to say K is 3 and N minus K minus 1 is equal to 41. These are the denominator degrees of freedom we'll ultimately be using. We all have SS error for the complete model is 4675.171. And mean square error, MSE, for the complete model, we have that is equal to, right next door, 114.0. 114.0. Okay, so what about the reduced model? The reduced model here has SS error equal to, our friend over here is SS error 13022.8, 13022.800. And then G, the number of variables in the reduced model is 1. K minus G is 3 minus 1. 2 degrees of freedom are changing between the two models. So here is our numerator, NUM degrees of freedom, and the denominator degrees of freedom is there. The F ratio that we said we're going to be calculating, F, is equal to the sums of squares error for the reduced model minus SS error for the complete model over K minus G, or delta degrees of freedom. Okay, that's also called delta degrees of freedom. Over then MSE for the complete model. Here we've got our friends 13022.800 minus 4675.171 over then 2 over the whole thing is over 114.0. So that is an F number. Do I have the, well, okay, I'm gonna calculate that F ratio a little bit differently. Well, one of you works at this by hand. The way I'm gonna calculate it is to turn it. The way I'm gonna calculate this is to work with the same data and refit my model just a hair differently. The model I'm going to fit in my fit model, I'm going to say prestige levels depend on income, and I'm just going to put in type. That's not the parameterization that we have as an indicator function parameterization. That is just saying, hey, let's fit across the three types. If I were to run that analysis, we get a p-value for type, as well as, and the p-value for type is within the effects test. And that is what I claim you should be getting as the ratio for your F right here. The claim is we should have an F ratio for type of 36.6. Ish. I guess there's maybe a little bit of rounding going on here when the software reports MSE of 114, but that should be about 36 or so. We can get a p-value from that 36 using our friend, the p-value calculator. And did any of you get that 36.6-ish?
Yes.
Perfect. Thank you. So I'm going to sort of save this, boom, and then clear it. And note within class for the day, there's this thing called a p-value calculator. I'm going to go ahead and just download it and just open it right up. And for your situation that you find yourself in, we have a F ratio, which we said was 36.6. Yeah. We had a change in degrees of freedom between our two models. Well, we had 3 to 1. That's a 2 degrees of freedom change. And we originally had 41 degrees of freedom for error. That is the denominator, or error degrees of freedom, 41. And we get a p-value of, in this case, well, okay, notice it says 7.58. That's like times 10 to the negative 10. That's really small. That's less than 0.0001. So we could get an exact p-value from our F ratio via this p-value calculator. Okay, so we got two separate approaches that you could use. One of which seems silly to me. We could go through all of the work of this partial F test, fit 1, 2 models side by side, and excuse me. And after we have these 2 models side by side, we could compare them literally with this test statistic F, the difference of the degrees of freedom, standardized to put it in a constant on a known ruler, a ruler that gives us a p-value. Or if you prefer, you could just go ahead and use the categorical version of type here. And if you fit the categorical version, you're home free. It gives you the exact same answer anyway. So you might be wondering, why the heck would I ask you to do this? Well, there are some situations where a partial F test will answer the question that you have when you couldn't answer it just by fitting the categorical predictor. Let's try 3 models and compare them. And let's work with the same data. I'm thinking perhaps my occupational prestige, boom, could be based on the income. Well, we're pretty sure that there's a slope there. Maybe there is a type effect, and perhaps there's even an interaction between type and income, I could cross that. I could fit a model with 1, 2, 3 trend lines that have 3 distinct slopes, run that. 3 different slopes for my 3 different groups. And an alternative model that I might want to consider instead is 1 trend line with 1 slope for the 1 group. Now you're sort of thinking, you already know from your explorations that you don't need that. You would prefer a model with the different groups. But if I were to say, let's fit a simpler, far simpler model, recall that, without an interaction and without even a difference across the types, could we compare these 2 models? And the answer is, heck yeah, we can. It's easy. With a partial F test, you could fit 1 trend line model versus a 3 trend line model, where the 1 trend line is compared to all of a sudden 3 trend lines with 3 separate slopes possible. If we go from 70 to 90% R squared, that seems like a win. But the analysis of variance for this 1 trend line model says, well, 1 trend line is really clearly evident. Here we're saying, well, we like our model now, but we're saying only at least one of the variables is important. Maybe it was the income that was important. Okay. Are we better off now with our interaction parameter estimates? The type blue collar, the type professional, the income interaction with blue collar, the income interaction with professional, with these 1, 2, 3, 4 variables added in to a model that effectively had an intercept and a slope for income. Those 2 stay the same. If we have a model with 1, 2, 3, 4 more parameters, I'm thinking I could compare the 2 models, literally my sum of squares here, compared to that sum of squares error, divide through by the number of parameters that are changed between the 2 models. We're going from a model of 5 to a model with 1 parameter. That's a drop of 4 degrees of freedom. You could tell me at the end of the day whether any of those 4 variables are statistically related to the response. Okay, that's a lot of content about one particular procedure. And it was a little bit of a diversion, but it ties to some of the recent labs you've done, and it needs to precede a later analysis where next week, where we're going to really say, hey, across these 3 variables, none of which seem to be related individually with t-tests to the response, is at least one of them really related to the response? If they're all correlated variables with each other, you might not see in individual t-tests that any of those variables would be necessary. But if you were to be careful, you might say across a partial F test, at least one of them is helpful for you. You might not be able to tell me which one it is, but at least one of them you could spot as being helpful via procedure like this. Okay, that seems a great place to stop for the day, other than, well, you guys have a lab that corresponds to San Luis Obispo housing data and different neighborhoods. And in the different neighborhoods, I betcha that you would pay a different rate per square foot to sort of get you primed for this. If you were to go to Turlock, California, and compare a home with 2,000 square feet to a home with 1,900 square feet, it's like 100 square foot larger. The amount that you pay extra in Turlock for that extra 100 square feet, it'd be one amount. But in San Francisco, that same 100 square foot extra will be probably a much larger premium that you would have to pay. So the slope might be different in some neighborhoods than in others, relating the size of the home to the price of the home. And you're going to be exploring that in the context of the lab, as well as looking at these indicator variables and coming to terms with what our effects test really is, and then also using the partial F test. But that's for the lab. So any questions before we call it a day and I stop recording? Okay, so I'm gonna call it a day, stop recording, boom. And